Okay, in this screencast, we're just going to quickly review some of the major forces that we might be dealing with when applying Newton's second law. We're going to do four major forces, and by far this is not the only forces that can exist, but they're very common in the type of applications we're going to do. Now, the first force we're going to do is the only force that we're dealing with right now that acts as at a distance, and that is the gravitational force. As we've already discussed in class, any two masses, any two objects that have the property of mass will attract each other. And the strength of attraction depends on the product of their masses and inversely proportional to the distance between the centers squared. And the constant of proportionality is this thing called the universal gravitational constant. It's a very small number, and that's why we don't feel a gravitational force between people that are standing next to us. But the Earth is so big, when you multiply these numbers together, even though the radius is big, you get a big enough force to be pulled towards the Earth. Now, at the surface of the Earth, we know that our weight is our mass times the rate, times g. G can be expressed not just in terms of meters per second squared, but in newtons of force per kilogram of mass. So for example, if I have a 1 kilogram mass, G is 9.8 newtons of force per kilogram. I weigh 9.8 newtons. If I'm a 2 kilogram mass, G is 9.8 newtons per kilogram. That means I have a 19.6 Newton force acting on me at the surface of the Earth. Now, this value G only applies right near the surface of the Earth, and we can prove that by setting weight equal to the gravitational force between any mass and the Earth's mass. And if you're standing on the surface of the Earth, the r is the radius of the Earth. You divide both sides by m, divide weight by m, and you get g, and this value, g, equals big G times m Earth over radius of Earth squared. That will give you 9.8 meter per second squared if you're at the surface of the Earth. If your radius is bigger, G will be smaller. So if you want to measure somebody's weight right on the surface of the Earth, you just multiply the mass times the acceleration rate of gravity, or the force per mass, which is 9.8 newtons per kilogram, and someone with a 70 kilogram mass will weigh 686 newtons on Earth. If you're at some elevation, like in a hot air balloon way up high, it might be slightly less. If you're in a place where G is much lower, like Mars, which is 1/3 the G of Earth, you'd weigh 1/3 what you do on Earth. And on the moon, it's 1/6. But anyway, in a lot of the problems we're going to do, you just have a mass sitting on Earth, so there's going to be a downward force acting on that mass straight towards the center of the Earth of m times g. So that's our only non-contact force that we're going to be dealing with. Although we did say that all the contact forces are really non-contact forces, but we'll treat them as if they really were contact forces. So the other force that we're going to use a lot is called the normal force. The normal force is a force that exists perpendicular between two surfaces that keep the two surfaces from falling through each other. So if I put a box on a table, gravity wants to pull it down to the center of the Earth. The table says no, and it exerts an upward normal force to keep it balanced. Now, the normal force, well, in this example, will equal the weight force because those are the only two forces acting. But if I add other forces, they won't necessarily equal to each other, or if I change the geometry. So here the net force is n minus mg, n minus mg. They're not accelerating, so n equals mg. In the case where I apply an upward force like this, and you break this force into components, you can see the upward forces, there's two now instead of just n. So to balance mg, n doesn't have to be as big, because you have this component of upward force due to the applied force. In the horizontal direction, this force is unbalanced, and this object will accelerate to the right. So go ahead and check out the equation here, and you can see basically what I'm saying, that the vertical forces are n minus mg plus f sine theta. And so n is going to be less than mg. If I put the object on a situation like this, I put this thing on an elevator, and the elevator is accelerating upward, then N won't be the same as mg either, because this surface has to push harder on the block than gravity is pulling down in order to accelerate it upward. So in this case, the net force is N minus mg. N is bigger than mg, so we get N minus mg equals ma. So the normal force is simply a force existing between two surfaces, and a lot of times we see that it's just something sitting on a flat surface. The normal force is just balancing the gravity force. But that's not always the case. And in fact, if you were in this situation, you know the normal force is bigger than the weight force if you were to accelerate upward in the elevator, because you'd feel a stronger normal force. Your feet feel more tied to the floor when the elevator is accelerating upward. And the normal force might be at an angle to the gravity force. So in this case, the normal force only has to balance this component of the gravity force, and the unbalanced part of the force of gravity is going to be the thing that accelerates you down the ramp. So in the vertical direction, this should say cosine right there, the normal force up is equal to the mg cosine theta force down. This force is uncanceled, so in the x direction, the force of gravity in the x direction is mg sine theta. If this angle is theta, it's the same angle as this, and you can prove it to yourself by doing a little geometry. And so this equals ma, so I could determine the acceleration in the x direction because this is the only force in the x direction. So that is the gravity force and the normal force. Now, we have a separate screencast to discuss friction forces. Friction forces are also surface forces that act between two surfaces that resist the sliding motion between those two surfaces. And to go in more detail on those friction forces, that will be the other screencast. So finally, there's one more force that we're going to use commonly, and that sometimes we'll be pulling things with a rope. And when we pull things with a rope, there is a tension in the rope, and when that rope is attached to an object, it will exert a force because the rope is being stressed. So on this guy right here, he's pulling the rope, and that is tensing up the rope and therefore applying a forward and upward force on the car. And there is a resisting force of the rope back on him. Just like in a tug of war, each side feels a force pulling them towards the other side. Now, if this rope is relatively light, we can assume that those two forces on either side are equal to each other and act sort of as action-reaction forces. If I don't care about his motion, doesn't really matter, then I can just take this force and it'll be one of the forces acting on this car. And so I could have, for example, an object that's attached to a rope and this whole system is accelerating upward, or in this case, I guess it's not. So the net force is T minus mg, and in this case, T equals mg. In this case right here, I could have a tension force on this elevator, or on this block right here. The elevator is accelerating upward. So just like with the normal force acting on the floor, it acts exactly the same way. The rope pulls up at a greater force than the weight pulls down. So my net force is T minus mg, and that equals ma. And if I know the acceleration, I could find out what the tension is. If I know the tension, I could find out the acceleration. But again, this is just a force that exists when some kind of rope or cord or something pulls. There's always a pulling force. And finally, we can have things that are in equilibrium. And we'll talk a little bit more of that later, but this will just be a quick example. I know in this case right here that the forces all cancel out because this thing is in equilibrium. So if I take the junction point where all the forces act, I've got a tension force this way, a tension force that way, and a weight force that way. And if I break the tension force into components, then I can determine what that tension is, because the two y components have to balance the gravity force, and the two x components are going to cancel each other out. Now this is a little bit more complicated when it's not symmetrical, but just go ahead and have a look at this slide and see if you can figure out how you determine each one of these two tension forces. Because it's not accelerating and the net force equals 0, we can take a junction point at the mass where all the forces appear to be acting. So go ahead and reason your way through this, and then we will say that that's a good screencast for today. So again, we'll be using a force of gravity a lot of times. That'll be the weight force acting on an object. We'll be looking at normal forces where objects surfaces push perpendicularly on each other. Friction forces are between surfaces that resist the sliding between them. And tension forces are forces that are when a cord or a rope is attached to you or an object and pulling on that object, applying a force to that object. All right, so that is a basic introduction to these basic forces that we're going to now apply to problems where we have multiple forces, just like in the ones we've been seeing, and we're going to more formally figure out how to set up the free body diagrams and solve for the accelerations and unknown forces and such. Okay, so again, I've got to turn this thing off.